Hi everyone, welcome back to the channel. So for any analog circuit, we mostly consider three region of transistors. One is called the cutoff region, linear region, and the saturation region. And we also assume in a cutoff region the drain current is zero, but which is actually not true. So we will see in today's video the concept called the weak inversion. So in weak inversion is same as the cutoff region where the gate to source voltage is less than the threshold voltage. Conversely, in strong inversion or in linear region, we consider that the VGS is greater than the threshold voltage, where the drain current is not zero. Here, drain current is equals to zero or it is actually very small. So most of the cases we consider it is equals to zero, and that is a very good approximation. But in today's video, we will see it is not zero. Okay, let us consider these two diagrams where whenever we have the gate to source voltage greater than the threshold voltage, we have very strong electric field in these regions. It means we have a very plenty number of inversion charges in this region, which actually contribute a huge drain current compared to this condition. In this condition, we call this a cutoff situation. Here, the drain current is very small, but it is actually not zero. Why? Because this VGS is not zero, or if you look at the gate to the body voltage, it is actually not zero. It is small but not zero, and because of that, we have a very weak electric field over here, and we have very less number of free carriers here. And because of that, drain current is very small. Now, as far as analog circuit is concerned, we can remember this equation where the drain current is represented by this equation. Here ID0 is a constant and it is dependent on the VGS, the threshold voltage VTH, and the thermal voltage VT. Also note that M is the non-ideality factor over here. It is close to 1 and 2, and it is also dependent on the drain to source voltage. Now, if you consider the drain to source voltage is much higher than the M times VT, that time you can ignore this part and you can approximate this ID as this. And as you can see, there is no dependency of VDS in this equation. It means if you calculate R0, which will actually be very large. Similarly, from this equation, you can calculate the GM, which is actually, you will get it as ID by M times VT. Remember, this VT is basically your thermal voltage. Now quickly compare this strong inversion GM and the weak inversion GM. In strong inversion, the GM is basically, let's say, 2ID by VGS minus VTH. Instead of GM, you can also consider GM by ID, which is also a very good metric. So basically, it will tell you what exactly is given GM for a given ID current. Okay, so the GM by ID is basically here VGS minus VTH by 2, which is basically VOD by 2. Here it is 1 over M times VT. Let's say M equals to 1 and VT equals to 25 millivolt. We know it is 25 millivolt at room temperature, and in most of the cases VOD is at least 200 or close to 200 millivolt minimum. So if I put all these values over here, we'll get in weak inversion the GM by ID is basically 1 by 25 millivolt, and here in strong inversion it is 1 by 100 millivolt, where this quantity, as you can see, is 4 times higher than this quantity in strong inversion. So in general, the GM in strong inversion is much higher than the GM in weak inversion. But there is some limitations. What is that? Let's say we have two situations. Here I have biased this transistor using the current source I0. This is in strong inversion, let's say. And this transistor M2 I have biased with the same current I0, and it is in weak inversion. Clearly, we know that equation of drain current, in this case I0, is basically half mu n C ox W by L VGS minus VTH. If you want to reduce VGS, you definitely have to increase W by L ratio. So for weak inversion, the W by L ratio is much higher than the W by L ratio in strong inversion, for a given current I naught. It means it will drastically increase the gate capacitance or this drain capacitance or any node capacitance wherever we have these transistors. So it will actually slow down the circuit. The speed will go for a toss. Again, let's say you are biasing the same transistor M1, M0 and M0 here using a voltage source VGS1 here and VGS2 here, and let's say this is in weak inversion, this is in strong inversion. Definitely your we consider VGS2 much smaller than the VGS1 because we want this transistor to be in weak inversion, and because of that definitely this ID0 2 is much smaller than ID0 1. Again, if you compare, if your drain current reduces, your speed will again go for a toss.